So, so this week you have started learning about the control of manipulators. After a brief discussion about sensors and actuators, we have moved on to now how to control the motion of a manipulator or in general any robot. So I will primarily focus on the control systems part because like actuators and sensors, those are topics where you just have to pretty much read some information and know about it. They are very important part of a robot, no doubt about it, but we'll focus mostly on the control and development of the controller for a robot and the theory behind it. So let's get started. Okay, so manipulator. So few terms that we will regularly encounter in discussions about control is first is the system. What's your system? Right, that's one thing. Then there will be a controller, which basically inside it lies the whole control algorithm, and a system also can be shown as a part of system can be shown as a process in which there are certain inputs and outputs, right? Now you would have heard two types of control strategies. One is the open loop control and second is the closed loop control. So first we will see what do these two terminologies mean, and whenever you encounter or hear these terms, what idea do you get about the control structure that is in discussion. So first, let's a typical open loop control structure is that you you have a input which is the desired response of your system, right? Desired response, and this goes to your actuators. Then the actuators apply certain torques on your process or system, and you get the output, right? You get the output. Okay, so why it's called an open loop, it's pretty obvious that we are not taking the information about the output in order to adjust our input. So we are just trusting the uh, actuator inside or whatever is inside this block, right? Whether it be a motor or something, to produce a desired signal that is able to give me the desired response at the output, right? So example of an open loop device that works in open loop is a type of actuator called as a stepper motor, right? So an example of open loop control can be that let's say you want to track some velocity right? You give a velocity trajectory which is then converted into a voltage. This is velocity, which is then converted into a voltage trajectory. By voltage trajectory, I mean that there is some mapping, right? In this actuator block, there will be some mapping that in order to run at a certain speed, let's say theta dot, the voltage required will be some k times theta dot or some function of it, right? K times theta dot plus c, something like it, right? So accordingly, the motor will produce a voltage and it will send to the process, and process will give you the theta dot out, right? This is theta dot in. So this is open loop control, that we are just trying to modulate our response at the output by modulating the input. We are not including the information that what did we achieve at the output in deciding what is our control input. Okay, and once we say that, that makes it pretty clear that what will be the diagram or the scenario in the case of in case of closed loop control. So therein is the input. Let me draw it here. So closed loop control. So in this case, there is the input. Now from here is the what we call a block for comparison, right? Then the comparison goes to the controller, then controller gives the command to the actuator, the actuator sends that command to the process, the process generates an output, and that output is, firstly, that output should be, in order to use that output you have to measure it. So we have to take measurement and then put that measured output back into this comparison block, where the input and the measured output are compared, and accordingly, according to some law or some formulation, the control action is varied or changed, right? So here the control input at this stage takes into account what is my output at the previous stage. So at the control input at the current time step takes into account maybe just the previous output or what has been the historical outputs. So in some form it includes the information about the output also, and that's why this is called closed loop control. And this is the, like, mostly in most of the cases, this is the control that we will be using or is used, right? So in fact, most of the times when we say talk about control, it is understood that we are talking about closed loop control itself, right? So this is the standard thing to do, because of it has some obvious benefits, right? When you know that, when you take in information about your output also, then you can better modulate your input, right? So it has obvious advantages in compared to open loop control. And for controlling complicated systems such as robots, this is very much necessary to know about where the robot actually is, how fast it is actually moving, and all those kind of informations. So whatever that we see from here we will be building towards executing closed loop control strategies. All right. So any doubts still here?
Sir,
Yes, Karthik.
What does the process block do, sir? Like everything is
Process
taken
block
care
is
by.
basically yeah, I will tell you. So you can think of it as let's say it's a 2R manipulator, right? This actuator block I am drawing here, which gives me the joint torques, right? Tau 1 and tau 2. So torque is the input here, right? And fr- and in most of the cases there is a joint encoder placed at these joints. Joint encoder is a sensor. It's like there are various kinds of joint encoders, but it will mostly look like a small button kind of a thing which is placed on an electronic circuit, right? And it basically senses the it sends the position of the motor, right? So how far you have moved. So the process is basically when you apply this input, which is torque in this case, then how much have you moved. So quantities like theta, angle, velocity, maybe acceleration is not directly measured, so let's not write it here. So position and velocity, right? So these systems, what's the typical equation, right? Tau is equal to m, the mass matrix times the acceleration, the Coriolis and centrifugal terms, and the gravity terms, right? So once you know this, then you can calculate these theta double dots, then you can integrate to get theta dot, then you again integrate to get position. So doing the so this is, if you remember, is the forward dynamics. So forward dynamics is happening here, right? That given this force, what are my accelerations, velocities, and positions? So that's the output, and that's the thing we measure. That okay, I wanted to reach at 15 degrees, I reached 14.95 degrees, and I measure that, and accordingly I will maybe increase my torque by some amount, so that I reach as close as possible to 15 degrees, right? So the forward dynamics part is happening inside the process block here. Is it clear?
Yes, sir. So after the forward dynamics happened, then it checks for the error, sir. That's what
Yeah, so
measurement
not
error.
the error is not checked here, right? Here at this point it's that it's the sensor. Let's say the sensor is at this stage in this flow diagram. The joint encoder which I talked about, it's at this stage, and joint encoder which is attached near the motor, right? So that will sense and give us a measurement of the joint angle, right? So this measured joint angle, let me denote this measured quantity as theta hat and my input quantity as theta. Then the usual thing is to take the difference between them, right? A very common approach. So theta minus theta hat. So this comparison is happening here, you know, and then this difference is used. Maybe a simple way is to just scale it and add it to the torque, which is the proportional and derivative controller, where we will see. But it can be used in multiple ways. So here the comparison happens, then this error is fed. This is the error. This error is fed to the controller, and the controller takes appropriate actions in order to drive that error to zero. So the goal of the closed loop controller is to drive this error to zero. All the strategies that you will see, all the different controllers that you will see, they all have one ultimate goal, is to drive the error between the desired and the actual to zero, right?
Sir, so only the position and the velocity values are computed in the process block, and they are measured in the measurement block,
Like
sir.
yeah, not computed as such, because in reality, if it's not a simulation, right, if it's not a simulation, then it's you are applying torques on your actual hardware, right? So of course that hardware will move, right, on its own, in the sense that, let's say there is a 2R manipulator, and you apply certain torques to the joints, then the system moves, right? Because you actuated it. And now to know how much it moves, we have it has moved, we put in sensors, right? So in if this diagram is for a hardware, for an experimental thing, then the process block is your actual hardware, your actual robot, wherein you gave the torques, and now the robot moved, did its action in response to that actuation, and then you sense it that how much it moved. Okay, so let's say a simple example is, let's say there is a block, right? And maybe I want to drive this block to this position, some position. Now and the amount of force that I apply is proportional to how far is this block is from the desired position, let's say. Okay, so when it's far, I apply a certain force, right? When you apply a certain force, what will the block do? The block will actually move, right? It will move some distance in response to your force. Then, so that's what the process thing is doing. In simulation, you that's basically one step of the simulation. You basically do forward dynamics actually. In hardware, it's just like when you are applying force to a certain system, it will move, right? It will do its thing, and then it reaches a next state, and in that state you take measurements, and then again do the whole thing again. Did I
Yes,
clear
sir.
your point,
Yes,
Karthik?
yes. Action, the
Yeah,
action.
so on hardware it will be actual action. The robot that you, or the arm that you see moving, that's the thing that happened due to the application of torque, and that's the thing that happened in the process block, the actual motion.
Yes, sir. Got it, sir.
Okay, so now each aspect of it, like the controller aspect is the whole control theory, the measurement aspect is what you will hear as the estimation, so it's the state estimation theory. So each block in here is, a whole field in itself. So for now we will focus ourselves onto the control block, and before even discussing control strategies, we will first build the foundation in order to, how to analyze, or how to describe whether when a system is stable, unstable, when when the error goes to zero, when it will blow up, all these things. Because our goal is to design, again, let me write this. So the goal in all the cases, however complex or simple the controller is, the goal is to drive the error between the desired and reference to zero. Drive it to zero. We can never actually in reality make it zero, but we can make it practically, like you can make it zero. Okay, in all practical sense. So that's the thing. Oh, let me add few pages in here. So the example of control systems is everywhere around us, like let's say a water heater, right? A water heater which you switch on and it automatically cuts off at after, and it reaches a certain temperature. That's a control system in action, you know. So there are everywhere around you, you can see control systems in action. Anywhere you want to reach a desired speed, you reach that speed, you're automatically the control cuts off. So it's not that these advanced robots and all are the only ones using, controllers. The controllers may be sophisticated for these technologies, but the concept of controllers is there for all. Now, now all the text has gone below. Hmm. Okay. Yeah, we are good. Good to proceed ahead. So now what we will discuss is that we will take one of the simplest systems that exists, you know, and that we use to analyze these stability concepts. And that's our very familiar textbook example of a, might have guessed it, a spring, a block, a spring, a mass, and a damper, right? This is mass m, this is the spring constant k, this is the damper b. Just before we start, so you guys are aware of what's the purpose of adding a damper, like in general, just as a general knowledge, if you have not exactly solved the maths before, but just what's a damper used for?
No, sir. No, sir.
Okay, so like, have you seen those doors which, you know, when you pull and then you need not close it, they automatically slowly get to this neutral position where they get closed,
Yes, sir.
right? So in those doors you would have seen a pot kind of a thing, you know, either at top or at the bottom, if you have observed. So that's a kind of a damper, right? So basically, if you pull apart the door, and if there is just, so in order to close it, there should be some restoring force acting on the door, right? So let's say if there is a most simple door in which there is just a hinge and the door panel, right? So that door you have to manually close it, right, in order to bring it back to its original position. Now, in order to bring it to its position on its own, what will you add? You might add a spring, right? So whenever there is a spring, things come back to its, try the spring tries to come back to its natural position, the mean position, right? So this, when you will open the door, the spring will apply a restoring force on the door, right? And it will try to bring it back to its resting position, in which the spring is unstretched. Okay, now the thing is, if you would imagine, what will happen is that you pull apart the door and you leave it, and then you would imagine that you there could be a case that the spring takes few oscillations in order to, you know, finally rest at the neutral position. Are you getting like the example? If just
Yes, sir.
right, so the door will oscillate back and forth, and then slowly the oscillations will die down and it will rest at the neutral position. This behavior we don't want, right? That every time the door is swinging and then slowly dying down, we want that the door should slowly come to its resting position and stop there. So then we add one more element in that system, we add the damper, right? So what does it, and as we will see when we do the mathematics of it, we will see in what case do we can entirely eliminate the oscillations and the system will gradually just come to that neutral position without making any oscillations, right? So that's what we will see. So this was the case where we didn't need, yeah, right, over damping, exactly. So this is a case where I was trying to avoid using that term because I will use it when we do the mathematics behind it. But it's correct. The system is overdamped, and there are some cases in which we would like to have oscillations also. We won't want our system to just be overdamped, right? There might be some cases where the purpose itself is of the system is to oscillate. So there could be that those cases too. So we will start from the deriving the equations of motion of the system, right? And few assumptions are has to be made. First, this is frictionless. Okay, so the only forces acting on the block is the restoring force due to the spring and due to the damper. Now springs and dampers are also of many types, right? So we need to specify This is a linear spring. And this is also a, I think, viscous so dampers force, so springs restoring force is proportional to the displacement, right? And dampers, so let me write as F spring and this is F damper. So dampers force is proportional to the velocity. Okay, so the faster you go, the more damping you experience. So damping is like something like, a similar force is the drag force. So drag force is proportional to the speed at which you are going. So the faster you go, the more drag you experience, right? So if you draw the free body diagram of the block, okay, so let us mark the x position here. Let's mark this is the positive x direction, and let's say we displace the block slightly towards the right. Okay, so in that case, what are the forces that will be acting? So if you push the block to the right, the spring will try to push it back to the left. So F spring will act like this, and F damping will act like this. Okay, there is also the weight of the block acting, which in our case is getting supported by the normal reaction, and since there is no friction, so these are the external forces on the block, and this is what we call as the FBD of the system, free body diagram of the system. So for writing equations of motion, however complex the system is, the best thing to do is to draw the free body diagram. Okay, now and since this system has only translation, we can use our tried and tested F is equal to ma. So, and we take this right direction as positive. Okay, positive x-axis. So it will be like sum of all external forces, that is minus Fs minus Fd is equal to mass times acceleration, and acceleration is d2x by dt2. Okay, so spring force is, as I said, proportional to the displacement, so minus kx. Fd is bx dot, so this is the damping force, is equal to m, and this we can write concisely as mx double dot. Okay, so the equation of motion is mx double dot plus bx dot plus kx, right, and this is equal to 0. So this is the case when there are no other forces on the system than the spring and the damper. Okay, now so this is which type of equation? Firstly, since derivatives are involved here, this is a differential equation, right? Second thing, the highest order of differentiation involved here is 2, right? Order is 2, the highest order. So this is a second order differential equation. And third thing is that all the terms are linear, right? So this is a linear second order differential equation, and these equations are very well studied and we have closed form analytical solutions for these equations, right? So we can solve them analytically with pen and paper. We need not use numerical methods or a computer to find solution to these equations. Okay, so now our task is to find the response. So the term response means the how does the state evolve. State is denoted by the x vector mostly. How does the state evolve? Okay, so for that we would need to solve this differential equation, right? So how to solve mx double dot plus bx dot plus kx is equal to 0, right? And in order to get a unique solution, right, in order to get a unique solution, you will need two more conditions, right? So now two conditions, you can give either two conditions on the same side, that is at t is equal to 0, or you can give two conditions at two different times also. So that's a different discussion altogether. Like it's either differential equations are either initial value problems or boundary value problems or a mix of these also. So initial value problems are those in which for the state, for the variable involved, variable and its derivative, the initial value at some time that is given, usually time t is equal to 0. Boundary value problem is that the value of the variable at two different locations is given, right? So at the boundary of the domain in which you are solving that differential equation, right? So in our case, what we can specify, and it will make sense practically also, that we know the initial position and we know the initial velocity, right? So these are two boundary conditions. What are they called? Boundary conditions. Okay, and since both are given at t is equal to 0, this becomes an initial value problem. Okay, any doubt till here in boundary conditions? Okay. Okay, so moving on. Now the approach to solve this differential equation is that, and there is some reasoning behind it also, that we make a guess of the solution, right? How do we make guess? That by trying out some functions and seeing like which type of a function can satisfy, you know, this type of an equation, we come up with a guess for xt, and let that guess be an exponential function, right? So it's a exponential function of t and multiplied with a constant c, right? So this is our guess that the solution is of this type. Okay, now once we take this as a guess, we can compute few other quantities, like x dot is this, x double dot is this, Okay, now we put these values in the differential equation. Okay, so the equation was mx double dot plus bx dot plus cx is no plus kx is equal to 0. So x double dot, in place of that we will write m c s square now b c s e. Okay, so this is the form that we get. Now in this we see that e to the power st is common and c is also common. So it's c e to the power st times m s square plus bs plus k. Now if c is 0, then there is no need to find a solution. Like,
For ST is common, sir.
okay, I missed the c in this one because x I have defined as c times e to the power st, right? So I missed a c in the last term. So that's how c is also common. So now if c is set to be 0, then the solution is very trivial. Then the solution is 0 and we are not interested in a 0 solution, right? We need to find the non-zero response of the system. So, and e to the power st is the exponential function. So the exponential function either goes like this, or for negative it goes like this, right? So it's never like exactly 0. So this term cannot be equal to 0. So the only way this can be 0 is we set this thing exactly as 0. So this implies that ms square plus bs plus k is equal to 0. Now how will you solve this? Can you please tell? Can you please think and tell me how can we get solve it? Like what to solve for and how do we solve this? This equation. First think about what's a type of this equation.
Quadratic.
Yeah, this is a quadratic equation. So for quadratic equation we have the formula, closed form formula of the roots of the quadratic equation, right? So this quadratic equation we write, I denote the two roots, that's the maximum number of roots possible. So it's b by 2a and a is here m plus minus under root b square minus 4mk by, right? So these are the roots, and this equation has a special name in the differential equation literature. It's called the characteristic equation, because solving this equation basically solves the original differential equation, and this equation is a quadratic equation which we can solve very easily. So we transformed a somewhat intimidating looking differential equation in a very ordinary looking quadratic equation. And since everything is defined for that system, for the second order system, using quantities coming into in this equation. I think that's the reason it has been called as the characteristic equation. It defines what will be the characteristics of the system, right? So the roots. So now, whenever we solve a quadratic system, there are always three cases which can arise, and those three cases are based on what are the type of the roots. So if the roots are unique and not equal to each other, then there are two different solutions, right? So that's one case. The other is that both the roots are equal, right? And the third case is that
Roots are imaginary.
roots are imaginary, right? That can be that's like, okay, I think I mixed two things. So the roots can be either real or imaginary, that's one separation. And the roots can be distinct or equal, because roots can be equal in case of yeah, so roots cannot be equal in case of imaginary roots, because if they are equal, then the imaginary part also has to be equal. And in this case, if the roots are complex or imaginary, then the imaginary parts are conjugate of each other, right? So I will list them down, it will become much more clearer. So we can think in general terms, like we can first it depends on kind of analysis also, we want to do real roots, imaginary roots, and equal roots. So let's keep it like that. Okay, and that is being decided by the quantity under the root, square root, which is b square minus 4mk, the discriminant. Okay, so this discriminant b square minus 4mk. So if d is greater than 0, we have real and distinct roots. If d is equal to 0, we have real and equal roots. And if d is less than 0, we have imaginary roots. Cool. Now, we do not want to limit our analysis, or we did not set out to find out if roots of this equation are real or imaginary or equal. We wanted to find out what's the response of the original system. So we still need to further investigate, like what is the consequence of having these type of roots. Like if the characteristic equation has real and distinct roots, then what happens to the system? What happens when the roots of characteristic equation are real and 0, and what happens when they are imaginary? Okay. Okay, so next what we will see is that we will define two important quantities of the system. Of any second order system, these two quantities are the most crucial one. One is the natural frequency, noted as omega n, and this is square root of k by m. And the second is let me draw it once again. And the second term is the damping factor. This is b by 2 under root km. Okay, so first is the natural frequency. So natural frequency is the frequency at which the system will oscillate without any other external forcing, right? So if you just like, if think of a pendulum, and if you just slightly displace it from its mean position and let it go, then the frequency at which it oscillates, that's the natural frequency. Or in the case of a spring mass system, you slightly displace it from the mean position and leave it, then this is the natural frequency and root k by m. So for any system, however complicated it may be, we can find the natural frequency of the system. And the damping ratio is the number which quantifies whether, like, how much damping is present in the system. And we will see that based on this number, we can classify systems into underdamped, overdamped, and critically damped. Okay, so before this, what we had is that we found out the two roots of the system, which were this. Okay, now let's see case by case what will be the response, because that's the main thing that we set out to investigate. So first case is S1 is not equal to S2, and S1 may be real, imaginary. The case is S1 not equal to S2, right? In case of a complex number, complex number A is equal to complex number B if both the real part and the imaginary part are equal to each other, right? So I guess you are aware of that. So till now, so as of now, we are not restricting it whether the number is real or complex. If S1 is not equal to S2, then the response of the system can be written as the weighted sum of two exponentials, right? Because we assume the system as C times E ST, and S has two values, right? So the final outcome will be weighted average, sorry, not weighted, weighted sum. Weighted because each of the exponentials are getting multiplied by a certain number, that is C1 and C2, and this is the response. Okay, now, and then the second case, so here you see that there are two independent solutions. Now in the second case, when S1 is equal to S2, xt is given as C1 plus C2t e to the power st. Now in the second case, that's interesting because here we did not get in two linearly independent solutions from the very beginning, right? We had only one solution from the characteristic equation, but in order to find the other part of the solution, we found out a function which is linearly independent to the first solution, that is C1 times e to the power st, and the solution of that is multiplying the exponential with t, right? So it becomes C1 plus C2t times e to the power st. So this is the solution in the second scenario when S1 is equal to S2. Okay, now in the case where, okay, let's consider it like this. So how will we use the initial conditions? So let's say our initial conditions are x0 is equal to x0 and v0 is equal to v0. Okay, so let's say for xt and s1 is not equal to s2, then the scenario becomes x0 is equal to c1 and e to the power 0 is 1 plus c2 e to the power 0 is 1, so c1 plus c2, and x dot t is c1 s1 e to the power s1t plus c2 s2 e to the power s2t. So when you put t is equal to 0, the equation becomes c1 s1 plus c2 s2 is equal to whatever the value. So either it will be x0, here it will be v0. So you solve these two equations and get c1 and c2. Two equations, two variables, get c1 and c2. So get c1, c2 from here. Okay. Can you see my screen?
Yes, sir.
Okay. All right. So coming back to the two things that we defined here, the two quantities, and let's see what are the values this can take and what happens in which case. So this damping ratio, and this is the Greek letters, I think this is xi. So this is defined as the p2 under root km. Okay, and first case is when psi equal to 0, right? This is no damping, undamped, because this will happen when b is 0, right? So b is 0 means that we don't have a damper in our system. So in this case, when b is 0, what will be s1 and s2? So when b is 0, the first term is 0, and here also we have under root minus 4mk. So it will be, you can very easily see that we get imaginary roots, right? So s1 2 is 0 plus minus under root minus 4mk by 2m. Okay, so this will be 2 under root km by 2m plus minus and j. J here means imaginary number. Two will cancel out, and what you will get is right. This is what you will get, and if you see, this term will look familiar to you. This is what we defined as the natural frequency, isn't it? So the response in this case is C1, and what was the thing? E1 S1 T, right? So it will be e to the power j omega n t plus C2 e to the power minus j omega n t. This is the response for b equal to 0, the undamped case. Any doubts still here?
Sir,
Yes, Karthik.
just a small clarification, sir. I understood the example of a door which you have given, sir, for the damper. So the damper just prevents the oscillation, sir, when we release it.
Yeah, in that case, now since we have discussed these terms, and as I think Vaibhav mentioned, that in that case, the door case, the damper is chosen such that the system is over damped, right? And over damped case, I will just be discussing next, is when this xi term is greater than 1. Okay, so when you will be designing that damper, you will choose the damping of that damper in such a way that this xi comes out to be greater than 1, and in that case, the over damped case, the second order system shows no oscillations. So I will also sketch out typical responses. So the system dies down or goes to its steady state value without any oscillations. So it will be like, so the plot is, I will draw in a more proper way again, but it's something like this. It just dies down to its value. Okay, so in that case, the damper is chosen such that the system is over damped.
Okay, sir. Sir, so here when we take xi is equal to 0, it means the spring example which we have taken here. If the xi is 0, the spring normally behaves the way it just behaves normally.
Yeah. Xi 0
without
means that there is no damper. It's just a spring, and if it's just a spring, then there is, and if it's an we are considering an ideal situation. I mean that there are no other forces like drag, friction, and all to kill the oscillations. So in that scenario, if there is no damper and there is only a spring, then there will be oscillations, and the oscillations will continue infinitely, right? So if there is, in our case, the block, if there is just a spring and the surface is frictionless and there is no like air resistance and all, then if you just displace the block and leave it, then the block will keep on oscillating about its mean position till infinite time.
So this is a case where we have a block and a spring. That's it, no, sir?
Yeah. So
It's
there is, so we are discussing the general case when there is both spring and damper, but it's still interesting to know what happens when there is no damper. And it is expected that so as I will tell you, like the response that we got, so this is an oscillatory response, and how we will just like bring it into a form in which you will more clearly see that how this how this response is an oscillatory response. So let's in fact do that only next. So the way in which I have written the response right now, it's in terms of exponentials, right? But exponentials, in fact, exponentials, when their exponent is this thing is in like imaginary number, then it attains some extra meaning. So just an aside, could you please tell me, if I write e to the power I theta, then this is equal to, this is a special way to write a complex number. Do you guys are aware of this? You must have read this in your uh, like high school maths. Like this is cos theta plus, I'm mixing notation, so let me keep j as the imaginary thing. So j sin theta. Are you guys aware of this?
Yes, sir.
Yes.
Right, so this is
Heard
the
of it.
polar notation of complex numbers, right? And like generally, a more general is to write r times e j theta, where r is the magnitude, theta is the argument, right? So it's like this is the Argand plane, and if here is a complex number a plus jb, right, then the x-axis is the real axis, the y-axis is the imaginary axis, this is the imaginary axis, then this theta, so theta is tan inverse b by a, right? So and this distance is r, so r cos theta is equal to a, and b is equal to r sin theta, right? So it's r cos theta in real and j times r sin theta. Okay, so just an aside, like just to refresh your basic complex number notations. So using this information, what you can write here is basically write it in terms of sines and cosines. So the first term you can write, let's say c1 times cos omega and t plus j is the imaginary indicator, and sine omega and t. Okay, and then second is c2, and then again cos omega and t, because cos of minus theta is cos theta itself, and sine of minus theta is minus sine theta, so minus j sine omega and t, right? Now if you further group the terms of cosines and sines, then this will be c1 plus c2 cos omega and t, and plus c1 minus c2 sine omega and t. Okay, and further if we, let's say, denote this by maybe some other constant, just to write it more succinctly, this is p cos omega and t, and this is q sine omega and t, and of course I missed a j here. All right, so this is, from here you can see this is some oscillatory response because it has sines and cosines. Wherever you see sines and cosines, you can say that it's an oscillatory response. Okay, And now you can express these in multiple different ways. You can express the whole thing together in terms of a single sinusoid, something like this: a cos omega n t plus phi. There is a very standard way to express a sinusoidal. So natural frequency is omega, n, phi is the phase shift, right? A is the amplitude. So this is the response in undamped case. Undamped spring mass systems response. Okay, so very important. Now, in case of the damped system, I will not derive the whole thing, but I will just write if xi is not equal to 0, not equal to 0. Then in that case, xt is a e to the power minus let me check the expression once. What sigma here? So a to the power minus xi omega n and cos omega d t plus phi, wherein omega d is a new term which I am defining, that is omega n into 1 minus xi square. So few things to unpack here. Like, I have not discussed how we arrive on this, but still we can make all the important conclusions out of this. First thing, the amplitude. What can you say about this amplitude? Initially it was just a, now it's a times a exponential, and exponential has negative exponent, so it's a decaying exponential, right? So the amplitude is, what is happening, the amplitude is decaying, right? So let me see if there is a plot in here. Okay, I will draw it. So in the these are the sinusoids. This is the case when there is no damping. So whenever you see a plot where there is no decrease in the amplitude, that means there is no damping. And this is the, let's say, time, and this is x. So this is a response, no damping. Now can you guess what will be the case when there is damping? And damping is, this is between 0 to 1. That's the next case we are considering, right? I should mention here. So see this amplitude term. This is a fixed number multiplying to a decaying exponential function, right? So the amplitude, this very clearly shows is that the amplitude is decaying with time. What's happening? So first what we draw is that we draw the envelope of the amplitude. So this a into e to the power minus xi omega and t, this is something like this. That's how you, that's how we draw a decaying exponential, right? And since there is still a sinusoid term, so that means, so we have decaying amplitude and oscillations with damped frequency. So oscillations are also slower than before. All right. So and slowly you see they are dying down, something like this. Okay. And you see that this is called damped natural frequency. And as xi is between 0 to 1 in this case, so 1 minus xi square will be of course less than 1. So omega n is multiplied to a number less than 1, so omega d is less than omega n, right? And since omega d is less than omega n, the frequency of the oscillations also die down. Okay, so now the system is oscillating at a lower frequency, and also the amplitude of the oscillations is dying down with time. Any doubt in this case? This is the underdamped case where there are oscillations but the oscillations die down because of damping. Any doubts in the mathematical part or the physical intuition part? Okay.
Before
Yeah.
oscillations occur, we are providing a displacement to the system, isn't it?
Can you please repeat?
Before oscillations occur,
Uh-huh.
we ourselves provide some disturbance to the system.
Yes,
some
yes, yes.
displacement.
Yes, if you remember,
So,
I had mentioned that a common boundary condition is that we take x0 as 0 and v0 as some non-zero velocity, right? So at time t is equal to 0, I am giving some non-zero velocity to the system, and basically that's the energy that I am putting into the system, right? And therein starts the oscillations. Without
okay.
disturbing, the system will stay as it is. There will be no oscillations. Is your doubt clear?
Yes, sir. Let's continue. Then
Okay.
I will ask.
So we have seen the underdamped case. Now, the third case is a special case when xi is equal to 1. And in that case, the response is so we put xi is equal to 1 in the above equation. So what happens is, what you can see is in omega d times phi. That was the case, right? When xi is between 0 to 1. When xi is equal to 1, it means that b is equal to 2 under root km, because b by 2 under root km is xi, and if you square both sides, this is b square is equal to 4 km. This means that b square minus 4 km is 0. This means xi is equal to 1 relates to which case? When b square minus 4 km is 0, right? That means both roots are equal. So in that case, we, as we saw earlier, when both roots are equal, we get which solution? We get c1 plus c2t e to the power st, right? And since s in our case is minus b by 2m, so for our case xt, so this will not be valid, right? So this will not be valid because omega d is 0, and this type of solution is not, does not come out when xi is equal to 1. Omega d is 0 can indicate you that there are no oscillations. Okay, so xt is e to the power minus b by 2m t, right? So in case in this case there are no oscillations, and the system is basically coming down to its neutral position without any oscillations, right? And if this case, let me see if there is some information about it here. Yeah, critical damping you can see. Okay, so yeah, these plots I might not have drawn such accurately. Okay, so what is, can you see this tab which I am showing?
Yes, sir.
Okay, so this is responses, like various responses for varying different parameters, like varying b, here they are varying m, and I think somewhere with they vary k also. Yeah, so they vary k also. So initial condition, you see that x0 is 0 and v0 is 1, and m and b are fixed and k is now varied, right? So for each of these cases you can just qualitatively see also that, let's calculate the damping ratio for these cases. So let me just quickly write down these values there, or let me just take a snip of it and take it there. Oops, not good. Okay, no worries, I will, let's write this down. So v0 is equal to 1. We are not solving for entire xt, but we'll just calculate the damping ratios and see if, and just like convince ourselves more with these plots that the response that we are getting is as expected. And k is 3, 10, 100,000. Different values of k. So 3, 10, 100. Okay, Newton per meter. So xi is b by 2 under root km. So b is 2 under root k. Let us keep k as it is, m is 1, so this is 2 cancelled, so this is 1 by under root k. Okay, so let's quickly write the xi values. So xi, let us keep this as 1, 2, keep 100 as 3 and 1000 as 4. So xi1 will be 1 by k1, xi2 will be 1 by k2. So 1 by 3 is 0.33, and note that xi is a dimensionless number. It's a ratio. Then 1 by root 10, okay, not 1 by 3, it's 1 by root 3. Can you please calculate on your end also and let me know these values? 1 by root 3, it's 0.577. We'll calculate a couple of them and this is verify. So 0.577. This is which case? Between 0 to 1. So underdamped case. xi2 is 1 by root 10. Let me calculate it.
Point
0.316.
Point
316.
316. And then xi3 for 100 is 1 by 10, so 0.1. And then xi4 is 1 by root 1000. Can you tell me that too?
0.0316.
0316. Okay. So what we see that xi is decreasing as k increases, right? So as k increases, you can think that this b and k, they are having opposite effects on the damping factor. If damping is increasing, the xi will increase. If damping is fixed and we keep on increasing the stiffness, which is the k thing, the damping effect will be less. So without seeing any plots, if the system is same and if the initial conditions are the same, then in which case there would be like most highest magnitude of amplitude of oscillations, in which xi is the least, right? So the fourth case, and the frequency will also reduce the least in this case, in xi4 compared to xi1. So let me see where that screen was. Yeah, so yeah, that's the thing which you see, right? So in the fourth case, you see that the oscillation frequency is the highest, right, compared to third case. The oscillation frequency is quite less, like it almost dies down when it reaches till 4, right? And what about the amplitude? So amplitude is the least in uh, the fourth case, right? The k is equal to 1000. The amplitude is least because stiffness is very high, right? So you would imagine that for a given initial condition, due to very stiff spring, it will oscillate very less, right? So stiffness, so it's good that you develop this intuition that a very stiff system will displace less but oscillate very fast, right? And a less stiff system will be displaced more, the oscillation amplitude will be large, and compared to a more stiff system, the oscillation frequency will be less, because natural frequency is also under root k by m. So for the same mass, Higher the stiffness, higher the natural frequency, right? You can, maybe I will think of some example. Mm, 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 mm. Yeah, I mean, like, uh, okay, quick example is not coming to my mind, but you get the idea, right? Higher the stiffness, more the higher the frequency of the natural frequency of the oscillations, and even after that damping thing, the oscillations are still pretty high. The damping is also less in that case. The effective damping ratio is less. And in this scenario, right, so this is what it's written here. Increasing K, the system natural frequency increases while the damping ratio decreases. Okay. Now in this case, where again same initial conditions, mass is still 1 kg, we have now fixed K, but the B values are now being changed. Yeah, tuning fork is an example. Yeah, yeah, different, good example. Like different tuning forks you have used. So you might remember that a tuning fork, a smaller one, which used to be of smaller sizes, they oscillate much faster and produce a higher pitch vibrations or higher pitch sound also than the bigger ones, which displace more but they vibrate slowly. So yeah, that example works. Good that you brought that up. Okay, so in this case we are varying the damping value. So obviously, the if you would see here, k times m is 1, so 2 under root k times m is 2 only, so the xi will be b by 2 only. So we can directly see that damping ratio will be b by 2, and it will increase from this point 0.02 to 2. So the damping ratio is increasing from the first plot to the last plot, and that is also very visible in the nature of the response, the oscillations that occur, right? In the first plot for b is equal to 0.02, there are still like good in amplitude oscillations when we reach 40, but in the last case is significant because that's the case when b by 2, that is 2 by 2, that is 1, xi is 1. So this is the critical damping case which I was talking about. So it's, you see that the value, there is one like shoot to the amplitude, and then in the second itself it dies down, right? So this is the critical damping case. And why critical damping is important? Because most of the time when we will study about control laws and study about PID laws, we will try to bring the system, we will set the gain such that the system is critically damped so that oscillations die down quickly, right? And maybe we can see the third case in which mass is being varied, right? So now the k, and so what's the effect of changing the mass, right? We saw the effect of changing k, we saw the effect of changing the damping. Now how does mass affect the response for the same stiffness and damping, right? So again, for m is equal to 1, this is the critical damping case. So without much oscillations, it just dies down to the zero value. And interestingly, right, so what happens, m is equal to 5, m is equal to 5, mass increased, then m is equal to 50. Then let's calculate the damping ratios once for this case. And Okay. This is that case. Okay, we'll need to think about resonance also. So quick note about resonance. No, not resonance right now. Resonance is okay. We'll discuss resonance later. Let's do the calculations of the natural frequencies here. So M is 1, 5, 50, 500. 1, 5, 50, 500 kg. And B is 1, B is 2 and K is 1. So B is 2, K is 1. Okay, so Xi1 is B1 by 2. Okay, B is the same, so 2K M1. So B value will put 2 by 2 and K is 1, so this is effectively, so damping ratio here is effectively 1 by root M. So again, could you please quickly tell me the values? Xi2 will be 1 by root 5, Xi3 is 1 by root 50, and Xi4 is 1 by root 500. What we see is that Xi value is decreasing. Xi decreases. So Xi decreases means that omega d increases, right? Omega d increases and also amplitude dies slowly. So this should happen, right? This is our expectation that as Xi is falling down, omega d, which is omega n times under root 1 minus Xi square, so omega d will increase. So the oscillations should be at a higher frequency as we go from 1 to 4, and the amplitude should die slowly. And then let's see the plots here. So first is critical damping, all right. Second we have, in the second case there are some oscillations and then they die down. In the third case there are even more oscillations. However, interestingly, the fourth case, the amplitude is more, which makes sense, but the frequency is less. Okay. The natural frequency is also changing in this case, right? So natural frequency is also changing in this case. That we should remember, because natural frequency is omega n under root k by m. So as mass increases, the natural frequency is decreasing, right? So that's why basically there is a let us read about this. So the mass m affects all system parameters. As mass m is increased, the natural frequency decreases and the damping ratio also decreases, right? Which is what we saw. Okay, that under root k by m, so angular natural frequency will decrease and damping ratio also decreases. So the conclusion is that the mass is increased, the response characteristic time becomes longer, and simultaneously the response becomes more poorly damped, right, as mass is increased. And also there is note about that the amplitude of the transient is the response, the oscillatory response increases strongly with increase in mass, right? So why this case is slightly more complicated, or is that mass is affecting both the damping ratio also and the natural frequency also. In the two previous cases when we were varying just b and k, right, we were either varying damping ratio or either varying natural frequency. No, I think in the K case also, uh, natural frequency is also being varied under root K by M, right? Yeah, in this case also both are being varied. So that statement is not correct. But yeah, like in these cases when we are varying the mass, keeping K and B fixed, we need to be slightly more look closely to understand these patterns about like how the damping changes and how the natural frequency changes. And the last comment is that the amplitude of the transient increases strongly with increase in mass. So this amplitude, right, this amplitude, because for the same v0, for the same what, why will this increase? Because you are giving the same velocity to that mass, right? So the initial energy that you are putting is higher. For the same velocity, the kinetic energy that you are giving to the system is higher for the higher mass system, right? So half mv square is higher when mass is higher, and the maximum, like the amplitude that it will take will be also higher, because at the maximum amplitude, uh, or the maximum displacement, the block is at rest, and the entire kinetic energy is converted to the spring potential energy. So the higher energy that we give in, the more amplitude that the system will take. So that's the reason of this observation, that at m is equal to 500, the amplitude goes up to 20, right? But on the other hand, why the frequency decreased? Because the under root k by m natural frequency, that decreased the natural frequency itself. And even though the damping ratio decreased, right, damping ratio decreased because of b is equal to 1 by root m in this case, this frequency is still less than the frequency in this case, m is equal to 50 case. So I think this one was little bit confusing than the other two ones. But any questions regarding this? Let's think about these statements that I made, and if any doubts are there, then please ask. I'm happy to explain again. Okay, so I think you got the point, right? Okay, great. And I think what I was showing you is critical damping, I showed you. And finally, yeah, and finally we have the over damped case, in which the damping ratio is greater than 1, right? And this case is generally we are less interested in. uh, yeah, so these are typical few responses of over damped systems. You see that there are no oscillations, and you can see just an exponential decrease in the response. All right. And in fact, what you see is that, again, yeah, very important observation, which will also explain why we want to keep xi is equal to 1, not as high as possible, right? By just thinking that, okay, why not make our systems over damped, why not just increase damping a lot? No, it's not good. It's not good, because you see that the as you increase the damping, the amplitude it reaches does decrease, right? In the first case, it reaches up to zero point 0.4. In the fourth case, it reaches to 0.05. But the this value, and remember that our goal was to go to zero error as soon as possible, right? So I will tie this all up to, we'll tie this all up to the case when where we are controlling a system and we are driving the error to zero, right? And in that case, what will matter more is how fast are we driving to zero error, not like uh, for it's not, it does not matter much that how away we were from the error position at the beginning. So for the critical damp case, the first case, although the amplitude goes to 0.4, it is almost 0, like before 10, right? However, in the last case, when xi is 10, even at 20, right, even at 20, now this value is much bigger than what's the case for critical damping at 10, right? So this figure very clearly shows what's the reasoning for making our systems critically damped, that is keeping xi equal to 1. Any questions here?
Sir, in beginning, when you gave the example of a door,
Mm-hmm.
in that I think you made the displacement to the maximum and allowed the velocity to be zero and let the system come to its neutral point, isn't it?
Yeah. So that initial condition is, it's different from these initial conditions in for which these plots are made. So these plots are made that the system is at the mean position, that is x0 is equal to 0, in which the spring, let's say, is at its natural length, and you give a initial velocity. Another case could be that I displace the spring to a certain length, right, which is the case of the door opening case, in which I displace the door to a certain angle and then I let it go. So that's a different kind of a initial condition. But these remarks would still say the same.
Okay, sir.
Yeah, there is a difference in initial condition, very rightly pointed out. Uh, it's a displacement initial condition, and here there is a velocity initial condition. And initial conditions are of, like, can be of very different types. Uh, uh, there is what we also call as impulse kind of initial condition, in which there is a force which acts on the block for a very short time, right? Like impulsive force. Then what's the response of the system? So that's also very interesting to analyze the response of the system in when excited in very different ways. But these comments are independent of the initial conditions that we give, right?
Yes, sir.
Okay. Okay, so I will just write the last remark there, that on why we choose critical damping. So why critical, and that's why the name also, like critical damping. At xi is equal to 1, the system achieves steady state. When I mean steady state, it means that it's had achieved a point. It has achieved the state in which the values between, let's say, with time, they do not change, almost do not change, or change insignificantly. Achieves steady state in the shortest time duration, right? So just for reference, I will draw two plots. This is, let's say, 0, 10, 20, and so on. This is time, this is x, and if this is for xi is equal to 1, then for the same system, let's say for xi is equal to 10, not very accurate figures, but I'm just trying to put it here so that you get an idea while referring to them, and it will be like something like this. So still going towards 0. Okay, x and t. So this is over damped, this is critically damped. So I will close today's discussion at this point. What we saw today is that we started on our journey of manipulator control, and we analyzed second order systems. We formulated the second order differential equation. We solved it using the characteristic equation. We saw what are the different cases of roots, what kind of roots are possible, right? And what is the type of response in each case. We saw major two quantities of interest: the natural frequency, the damping ratio, and at different values of damping ratio, how does the system responds. The undamped case, in which damping ratio is 0, the underdamped case, in which damping ratio is between 0 to 1, and there are, so in undamped case there are oscillations with no decrease in amplitude. In the underdamped case there are again oscillations, but the amplitude decreases with time, right? And in the critically damped case, it's a special case in which xi is equal to 1 and the amplitudes die down the fastest. And in the overdamped case, again there are no oscillations, but the system takes longer time to come to the 0 position. So for designing our control systems, which will be equivalent to spring mass damper systems in many cases, we will choose values of the parameters, the gain parameters, such that the system is critically damped, so that our goal of driving the error to 0 is achieved in the fastest possible way. Okay, so we'll continue from this point in the next class, and we'll from at like in this discussion hour we just focused on a spring mass damper system, but how does this relate to the original problem of controlling the position or the velocity of a manipulator, that we will see in the next discussion hour, and maybe also solve a few questions. Okay, so thanks for joining, and we'll meet in the next week.
Thank you, sir.
Sir,
Yes, Karthik.
just a small doubt, sir.
Mm-hmm.
So what is the difference between it's not related to this topic, sir.
Mm-hmm.
Difference between a cubic polynomial and a cubic spline, sir. What is the difference
Yeah,
between?
so I think I mentioned it in some discussion hour. Spline is
No.
when you stitch multiple polynomials together. So spline is made up of more than one polynomials, and polynomial is just a single polynomial. So that's the difference.
when do we
Spline
use
is
this,
made of multiple pieces. Can you repeat?
so when do we use spline over polynomial, sir?
Yes, so you can think of that if you are using a spline, if you are using a cubic, let's say you want to represent the trajectory of a joint from 0 to let's say 10 seconds, right? If you just use a cubic spline, if you use just a cubic polynomial between 0 to 10 seconds, then cubic polynomials have 4 parameters, right? So, and sorry so a cubic polynomial has 4 parameters that can be set, and those will be set by, as we saw in the trajectory generation discussion hour, that by defining the velocity and the position at both the endpoints, we can uniquely identify the 4 parameters of the cubic spline. So you can just specify these 4 things for going from point A to point B, or for in the trajectory, just by giving just in these just four satisfying just four constraints, your degrees of freedom are, of that polynomial are gone. But in reality, you you would like your path to be in such a way that you can satisfy more constraints, right? You might want to move around some obstacles, you might want to go through some point, right? So you want more flexibility in your path. So for adding more flexibility in your path, you have to stitch in more polynomials. The higher the number of polynomials, the more shapes your path can take, right? So yeah, flick I mean flick, I guess by flick you mean some additional motion in between, right? Between point A and
Yes,
point
sir.
B, right? So yeah, these kind of things. So in order to make your trajectory, I think you can say flexible in some sense, or add more features into it, you will need more degrees of freedom. And by degrees of freedom, I don't mean degrees of freedom of the system. I mean more parameters of your trajectory. So that's why, and one uh, example, one solution could be to use even higher number of even higher degrees polynomials itself, like one polynomial but even higher degree. But that again is not a good solution. A better solution is to use maybe third order or fifth order polynomials, and use multiple of them. And this has also some other reasons when like piecewise we combine them, and for each of them we define some constraints, and we can easily like solve for four parameters for each of those cubic polynomials which are splined together. So basically that's the reason, because you want your trajectory to not just go from point A to point B, but also satisfy a few more things.
Yes, sir. Got it.
Okay.
Thank you, sir.
Okay, then we'll meet next week. Goodbye.